Welcome back to the second part of 1.3. So just to recap, we've looked at three ways now to find a limit as x approaches c. And this is if direct substitution doesn't work. These might be three ways that you can revert to try and help you out. So numerically, and what we mean by numerically is to use tables. Okay, so you try and find values that are close to that C value, as close as you can get without being there, and then see what the Y values are doing around that point. Graphically, pretty self-explanatory, just look at the graph. Analytically then, the two ways that we looked at other than direct substitution were using factoring and canceling. And then if we couldn't factor and cancel, we could rationalize. Another thing you could do is use some trig identities, which we will get to here today. But yeah. Now, these strategies are all well, but they might not always work. Sometimes you might get a graph that's just super weird and it's hard to look at and find the perfect window for on your calculator. Tables, you might get weird numbers again, like I said, and those can be a lot of work. So there's a fourth strategy, and it's a theorem, and it's called the squeeze theorem. This is where we try to compare a function to two other functions that we know the limits of by squeezing the first one in between them. So, for example, if we are looking at this graph here, we're trying to find the limit of this function f, and by just looking at it, it's hard for us to tell what that value would be. So we have this function that's less than it, so we'll call that function h of x. So if this function h of x is less than or equal to f of x is less than or equal to another function, if you're looking at this graph, we will call it g of x. I guess if I'm going by colors here, I should probably follow the right ones. Okay, so our function that we're trying to find the limit of is between these two. And then like at the c value, it's in the interval that we're looking at. If we know then that those two functions intersect at that x equals c value and those are the same limit, so the limit as x approaches c using g, and then the limit as x approaches c of h here, and those end up being the same limit, then we know the limit as x approaches c of f of x, the original function we were given, exists, and it's equal to that same limit as well. All right, now these theorems can get kind of wordy, so let's see how we might actually be able to use them. All right, so let's look at this first example here. F, G, and H are these three functions defined right here. I know they look kind of scary, but don't worry, we can handle this. Which of the inequalities here, 1, 2, or 3, can be used with the squeeze theorem to find the limit of the function as x approaches 0? So when we're squeezing them in between here, the limit as x approaches that c value of h and the limit as x approaches that c value of g has to be the same. So what we're going to be looking at here is, what does it make sense that, like, basically are these limits of the left-hand side and the right-hand side the same as x approaches 0? So that's what we're going to be trying to look for here to help us find which one will work out. So let's take a look at the first one. So what we're going to do, okay, in order for this to work, we're trying to approach 0. So we're going to look at the limit of the function as x approaches 0, like that. And let's see what it equals. Okay, so we've learned enough about limits analytically. Can we just plug 0 in there? Kind of looks like we can. So we end up getting 1/3, it looks like. All right, now if we test out the right-hand side there for 1/2, so the limit as x goes to 0 of 1/2, well, it's a constant. And if we looked at those properties, the limit of a constant is just that constant. So the limit on the left and right hand side, they aren't the same. 1/3 doesn't equal 1/2, so we know it can't be that. All right, so let's now see if we can find these other limits. So for part 2 here, the limit as x goes to 0 of negative x squared. Well, if we substitute that in, we get 0. All right, and then the limit of the right side here, limit as x goes to 0 of x squared is, 0. So those limits are the same, so then we could technically then assume, okay, well, since these values are the same, the limits as we go to 0 are the same on either side. That means the limit of g of x as x goes to 0 has to be 0 as well. We still have to test out this last one. So part 3, the limit as x goes to 0 of -1 over absolute value of x. Now, -1 over absolute value of x, that's going to be undefined at 0. And since this would just be 0 on the bottom, thinking back to kind of our pre-calc, that's going to be a vertical asymptote. So that's going to actually be a limit that does not exist. So squeezing between these two functions isn't going to be helpful at all because the limit is not going to exist because we end up getting 0 on the bottom no matter what. There's no factoring and canceling. We can't rationalize. This is technically a no calculator question, but if you do graph it, you can see there's a vertical asymptote there that goes up to infinity or down to -infinity. So since neither of those limits exist, we know it can't be 3. So our only option is that g of x could be squeezed between negative x squared and positive x squared because we get the same limit on either side as we go to 0. So that's one way we can use the squeeze theorem to verify what the limit of something is, especially a function that's kind of scary like this. All right, here's another way we can use the squeeze theorem. Let g and h be the functions defined by sine of pi over 2x plus 4 and this polynomial, -1/4 x cubed plus 3/4 x plus 9/2. If f is a function, now we know that f is squeezed between these two. For x is -1 to 2, so on the open interval, we know that works. So they've already fulfilled those for us. What is the limit as x approaches 1 of f of x? Well, in order to figure out the limit as x approaches 1 for the middle function, we have to verify that the limit as x approaches 1 of g of x and the limit of h of x as x approaches 1 is the same. Those two have to be the same. So what we're going to do is the limit as x approaches 1 of g of x, sine of pi over 2x plus 4. And this one we should be able to just use some direct substitution with. So sine of pi over 2 times 1, so just sine of pi over 2 plus 4. Sine of pi over 2, that's going to be up at the top of the circle, is 1. So this is 5. All right, now when we do the limit of h of x as x approaches 1, we're going to hope that we get 5. So limit as x approaches 1, -1/4 x cubed plus 3/4 x plus 9/2. And again, we can just do some direct substitution. There's nothing really fancy about this one. So when we put 1 in for x, we just get -1/4 plus 3/4 plus 9/2. So we get 1/4 plus 3/4, or -1/4 plus 3/4, that's 2/4, that's 1/2 plus 9/2, so 10/2, which lo and behold is 5. So since we got the limit of g of x as x goes to 1, limit of h of x as x goes to 1 are both 5, that means, dun, 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 so lovely when something comes together, limit as x approaches 1 of f of x, our mystery function, is equal to 5. Okay. So again, the squeeze theorem is really just using what we know about finding limits analytically to kind of think about them a little more deeply and try and apply them a little bit. All right, so here we go. We get to the trig. All right, and with trig, we have two special trig limits. And the reason we do these now where we're at is because you can use the squeeze theorem to prove these two limits, and it does help you get a little deeper understanding. I will make a video of that proof. It is not required of you to watch, but you can go back and look at it if you'd like to see the squeeze theorem being used even in another different way. But these are two limits you're going to have to memorize. They're always going to be this way. The limit as x goes to 0 of sine of x over x equals 1. And then the second one is the limit of 1 minus cosine x over x as x goes to 0 equals 0. Okay, now as you go through these, you also have to remember that other properties of limits will still apply. So when we're looking at example 1 here, limit of 3 times 1 minus cosine x over x as x goes to 0. Well, when you got a lot going on in here, I mean, we can see the 1 minus x over cosine x, so we know it's going to have to be 0, but then some people get a little caught up on what to do with that 3. Well, this is just scalar multiplication, so we can just take that 3 and multiply it by the limit as x goes to 0 of 1 minus cosine x over x. Okay, and we know that this limit as x goes to 0 of that function is always going to be 0. So this is really just 3 times 0, so 0. All right, next, limit as x goes to 0, 4 times sine squared over x. Again, scalar multiplication, just so I can focus on the limit on its own. I like to bring that scale out front. Okay. Now, looking at this one, you think, oh, it's sine x, oh, it's just going to be 1, so this is just going to be 4, right? Well, we also have to take into account the fact that this is sine squared. So I'm going to break this up into sine times sine. So we get 4 times the limit as x goes to 0 of sine times the limit as x goes to 0 of sine of x over x. So this sine of x times this sine of x is our sine squared on the top. All right, now here, for this first sine limit, let me maybe put brackets around this so you can see how they separate. This limit of sine of x, as x goes to 0, I can just use direct substitution, sine of 0. This limit, I can use my formula. Limit of sine of x over x as x goes to 0 is always 1. All right, let's see here, sine of 0 is 0. So 4 times 0 times 1, we get 0. All right, next. In number 3, 4, and 5, really, the trick here is understanding that as long as this value, what's inside of the sine function, and what's on the bottom match each other, if they have the same coefficient, your answer will always be 1, as long as the limit is going to 0. So here, this is the sine of 5x, but it's over 1x. We actually want this to be over a 5x, so the inside of the sine matches what's on the denominator. So in order to do that, I'm going to multiply the top and bottom of this function by 5. So 5 over 5. So I'm just multiplying by 1. Then what ends up happening is this 5 on top will become a scalar. So it's going to be 5 times the limit as x goes to 0 of sine of 5x over 5x. So since we multiplied by 1, we didn't actually change the value of it. We just made it look the way it needs to in order to be able to use the property. So now since this is sine of 5x over 5x, this matches this, we can say then that this is equal to 1. See, I still even need to practice with these. So this is really just 5 times 1, so 5. And kind of like innately, you can look at that and think, oh, well, yeah, that would make sense because these are both 5s. Duh. That would make sense, right? Instead of just being 1, the stuff inside is 5 times bigger, so it should be 5. But it's helpful to show the work so you understand why it's doing that. Number 4 looks kind of the same, and people on this one are tempted to try and get the inside here to be a 5x, but you can't really do that because you can't just put something inside of a sine function and it'll be the same, and you can keep everything the same. So an easy thing here is to remember that this 5 on the bottom is only attached to this x. So this is the same as saying 1/5 times sine of x over x. So this is really just scalar multiplication of 1/5. So it's just going to be 1/5 times the limit as x goes to 0 of sine over x. Okay, and since that's just scalar multiplication, we know that this limit is 1, so it's just going to be 1/5. All right, now number 5, we're still going to use the same idea, but now this brings in some of our properties of trig. So tangent of 2x and secant of 3x. Okay, we're going to want to kind of rewrite these in terms of sine and cosine. I think that's going to be the most helpful because we know limits, we know 2 special limits involving sine and cosine. So if we can get part of it to kind of look like one of our special trig limits, then we can probably make it work. So let's rewrite these out. So tangent of 2x is going to be sine over cosine. So sine of 2x over, cosine of 2x. All right, and then secant of 3x is going to be 1 over cosine of 3x. Okay, so let's do some rewriting here. Limit as x goes to 0. Let's see, sine, 2x. I better keep all of that straight. All right, sine of 2x over cosine of 2x over 6x times 1 over cosine 3x, so 6x over cosine 3x. Okay. All right, so let's, instead of having fractions within fractions here, let's multiply by the reciprocal and see what we can do. Limit as x approaches 0 of sine of 2x over cosine 2x times the reciprocal, cosine 3x over 6x. All right, so we are trying to get, at least the way I'm looking at it, a sine of x over x of some sort. So we have a sine of 2x, so we want to somehow have a 2x on the bottom. So let's manipulate this a little bit. Our limit is going to 0, so sine of 2x over 2x is going to be 1. So sine of 2x over 2x, okay. Now if we do that, that means now we're multiplying by a cosine of 3x over, we've taken out a 2x, so that leaves this 6x to now be a 3, and then we still have a cosine of 2x here, like that. Okay, all right. So now let's take a look. I'm going to keep my work down here. So now I have the limit as x goes to 0 of sine of 2x over 2x, which I know is going to be 1. Woohoo! And then let's see here, limit as x goes to 0 of cosine of 3x over 3 cosine 2x. All right, we've done some master manipulation here. All right, so I know that this one's 1. Well, can I use direct substitution here? Cosine of 0 is 1. So if I plug 0 in, I should be able to just directly substitute. So here I get cosine of 0 over 3 times cosine of 0. So I get 1 times 1/3. So I went through all of this, and just when you think it's not gonna work, we end up getting 1/3. So even though something looks kind of messy, try and like the trick here in calculus is use algebraic manipulation. You can take this 6x and split it up into 2x times 3 so that you can use that special trig limit that we just learned. And then you will probably end up with something you can just substitute in for. That'll work out. All right, lastly, I know we're getting kind of long here. These are just so much fun. I don't want to stop. I'm actually serious about that too. All right, so on number 6, I'll give you a little precursor here. We're not going to be using these special trig limits. This one is just here to help practice, giving you some time to use your trig identities because it's been a while since we've used those. So here, if we plug in pi over 4, cosine of pi over 4 and sine of pi over 4 are the same, so we get 0 on the bottom. So direct substitution won't work. So we're going to have to manipulate this somehow. So the trick here is to see, okay, we have a 2 cosine squared. Anytime I see a cosine squared or a sine squared, I automatically go to the Pythagorean identity that involves sine and cosine. So sine squared plus cosine squared equals 1. That's always a good one to remember. Now, since those equal 1, lo and behold, I have a 1 in my top here. So what we're going to do in that numerator is just do the limit as x goes to pi over 4, 2 cosine squared minus the equivalent to 1 is sine squared plus cosine squared. So we're replacing that 1 with sine squared plus cosine squared all over cosine x minus sine x. And you're thinking, why did you just make that more complicated? No, there's more going on. I don't want to keep going. All right, well, if we distribute this negative, we end up with 2 cosine squareds minus 1 cosine squared. So on the top, we're left with, and maybe some of you are kind of seeing where I'm going with this, we end up with just 1 cosine squared minus sine squared over cosine minus sine. All right. Now, trig functions, imagine this is just what u squared minus v squared, we'll say, on the top. That's the difference of squares. We would write that as u minus v times u plus v, right? So this follows that same logic. So the limit as, x approaches pi over 4. And now our top becomes cosine minus sine times cosine plus sine all over cosine minus sine. All right, now the nice thing here is cosine minus sine, common factors, they end up canceling. That's equal to 1. So we are left with the limit as x goes to pi over 4 of cosine plus sine. And now we can just use our direct substitution. When we do that, we end up with, if my page will extend for me. It just did it like 4 times. There we go. We end up with cosine of pi over 4 plus sine of pi over 4. And if you remember what cosine of pi over 4 is, that's the one where they're both the same, root 2 over 2 plus root 2 over 2. So we have a half root 2 plus a half root 2. You should just end up with 1 root 2. Phew! Again, all that work. And it's so satisfying when you get an answer that's like, oh, it's so nice, it makes sense. All right, so you're going to want to practice these. Again, don't forget your Pythagorean identities. If you need to pull out that formula sheet from pre-calc to help you remember them, please do that or find them somewhere online. You will not get those on your AP test, but as you're practicing, it will be helpful to use those. Happy practicing, and don't forget about your LT check.